afternoon, everybody. After a couple of sessions there on profiling of your applications, the next talk is all about debugging. So here is as everyone has always said in the past, no one cares how quickly you can compute the wrong answer. So hopefully I'm here now to give you some advice on how you might cope if you get into the situation, heaven forbid, where actually you had a bug in your software. So just a word of introduction. I'm David Lecomber. I'm one of the founders of Allinea Software. What we do is development tools for HPC, and the one I'm here to talk about today is Allinea DDT, which is our debugger, which is installed on Mira and Titan, two systems that hopefully I'll use today. And as a whole, what we try and do is make HPC easy to use. If you can think of that friendly sort of environment that people are used to programming in other platforms for, such as, they'll bring up a nice GUI and they can type away and they can do their debugging and everything. And imagine what HPC would be like if it looked a bit like that. Well, that's what we try and do, and as part of that we have two products. One's DDT, the debugger, and the second one is MAP. And those are scalable tools that actually scale to the full size of the system. So with DDT it's the debugger, and with MAP it's a profiling tool, and put the two together and you have a nice integrated way of developing and improving your code that you use in HPC. In terms of where you might also come across our products, if you use any of the other major national sites, then you probably see at least DDT on there. Allinea MAP is actually quite new. We only released it about 4 months ago, but it's already in a number of the labs already. But we have users from across the globe really who are using DDT now because of the scalability of it and ease of use. Moving on from those sort of marketing slides, let's actually talk about some of these large machines. This is the extreme scale workshop. So what do we mean by extreme? Well, every time I think of extreme, I think, a few years ago, Petascale was extreme. And before that, Terascale was extreme. Extreme is just a word, and the definition of it actually changes all the time. So let's look at where we are today in terms of extreme machines. There's always been a number one, and the number of cores in that has been growing. I've had to put a logarithmic scale on this, even though I'm only going back 4 years. So you look at this straight line, almost straight line graph of 3 years ago, or rather 4 full years ago of that would be, I think it was Titan there at the number 1 spot. Oh, sorry, Jaguar at the number 1 spot there with just over 200,000 cores. And, over time that shifted to about 600,000 cores in the number 1 system in Japan, followed by Sequoia briefly. And then finally, the most recent, the Chinese system of something like 3 million cores. So machines are getting a lot bigger. It's been a trend, it's been carrying on for years. But what I also like to do is think, well, there's only one number 1 system in the world. What's the impact of sort of this extreme stuff on the rest of the world? And so you go down and look at the number 100 system, and you see that, yes, 4 years ago, if you wanted the number 100 spot on the top 500 list, you probably had to have 10,000 cores. Now, I think you've got to have something of the order of, I think it's about 32 to 40,000 cores to reach that spot. And then right at the very bottom, if you want to book a place on that top 500 list, you could get away with about 4,000 cores 4 years ago, but now you've got to be something like 16,000 cores, maybe that would be. So HPC machines of over 10,000 cores are not just rare. They're not, they're not rare anymore. They're everywhere now. So, there's at least 500 machines of that size. So the necessary, the corollary of that is that if we consider ourselves to be involved in HPC at all, then our software is surely going to need to use that many cores, or at least a very substantial proportion of that. So as the machine sizes explode, so does the scale at which your software needs to run. Which brings along some challenges for us all. Yeah, some software challenges. You cannot just put an extra flag to the compiler and expect everything to work. Well, it has to be said, there's some pretty good transformations you can get out of a modern compiler these days. The difference between some of the commercial and open source ones can be quite substantial. You might But that's still not going to be enough. You do have to restructure your code to cope for performance, to get that performance out at the extreme. You know, restructuring to get the most out of SIMD parallelism, vectorization on the Intel Xeon Phi, for example. Sometimes you have to do more fundamental changes as you try and take your code to something extreme. It may be that the whole basis of the maths, there's another way of calculating something that has a less computationally intensive or a less communication intensive way of dealing with a problem. And as you get down to this very fine-grained parallelism that you might have seen in the GPUs, or you might need to use to exploit vectorization, then it actually turns out you have to look back in some very old literature and bring up some PRAM algorithms from the 1980s where there was roughly one processing element per piece of data. And it's interesting to see some of the sort of algorithms being reused, like bitonic sorting and sorting networks that were all the rage in the early 80s, now appearing in people's applications that are using on GPUs and on Xeon Phis. So there's a lot of changes you're going to have to make to your software to run on this generation of system and the next. But that then makes us look at the topic of programmer efficiency. You know, we can't just rely on one sort of simple piece of code just running MPI. We've got to add something in there like GPU directives or perhaps offload directives. We've got to the situation where the performance trade-offs from doing those kinds of things are harder to understand than they've ever been. All the different hierarchies of memory, transferring data from one thing to another, and so on. It's getting rather complicated. And as you've made your code more complicated, then the software bugs are most likely going to be harder to fix. So let's take a look at what bugs could actually mean. And so as long as there has been programming, there has been software bugs of one form or another, right back from Grace Hopper in the middle there, detecting the physical bug inside a machine, a MOF on a relay. And there are bugs come in many shapes and sizes. This one is a data kind of bug. It was a company that does software verification, sent me an email and told me my phone number was 4.4 times 10 to the 11. Yeah, that's the UK code, international code, followed by our office number. You know, it happens in many ways that an application is going to misbehave. You know, you've probably seen a few of those coming out of a code on a Linux machine where it just crashes, and that's the Intel compilers sort of error thing at the error handler. But then some of the results of them, I love some of the ones you can pick out from Wikipedia. So I think back in the 90s there was a plane that was taken on a test flight, its first ever test flight, went across the equator, navigation system said, hang on, this doesn't look right, flipped the plane upside down. Rockets blowing up, that's happened more than once, but then more recently, I think it's one of the most recent jets in the sort of early 2000s, first went past the international date line, and the navigation systems weren't very happy either, and so they kind of shut off, and it had to follow a very slow tanker back to base. So bugs have been around for a long time, and they will continue to be around. So it's very helpful to be able to define and understand what a bug is. So it's always appropriate to get some physics terms in there. So the Bohr bug, steady, dependable, reliable, predictable. The Heisenbug is the one where it vanishes as you try to debug. They happen quite a lot. The Mandelbug, now these are really complex, obscure, beautiful bugs. They look chaotic, but in reality, what's behind them is always something very simple. My favorite is the Schrödinger bug, and I do believe these exist. You've got a program, it works, it's always worked. Someone reads that source file, and then the program stops working because they declare it could never have worked. So how do we deal with bugs in practice? Well, this is debugging in practice, and it's unfortunate. I mean, there are a lot of people still use printf for their debugging. Hands up who's used printf in their debugging. Hands up who still uses printf in their debugging. Okay, so it's quite common. So we know what to do. We run our code, it crashes. we have a hypothesis about why it crashed. So we insert a print statement, we compile it up, we run it again. And you can never get it right the first time, so you do that again. You have another hypothesis because you weren't right the first time. You insert another print statement, you compile, you run, you're round and round. That's a little bit time consuming. Go back. Where is the graphic gone? There's the graphic. And it won't appear, it just doesn't want to appear. It's not a bug, it's just my bad use of PowerPoint. So if you consider what's wrong with print statements, you can't print as soon as your program crashes because it's too late then. So you can never get the exact moment of a crash. The way you do a debugging with printf is to insert these messages saying, I'm here, the value of this is that, and it's iterative because you imagine trying to find essentially a crossing point. It's like finding, it's analogous to bisection root finding. You're trying to find this point, but if this is the line of code across here, then you insert a print statement here, you miss it because it doesn't come out when you run the program. So you go back, you bisect, you go half the distance, perhaps you put the print statement there, and again, it does appear, so therefore you've got to go in the other direction a little bit, put the print statement, and back and forth, back and forth. That has many problems, not least the fact that, that it's slow because you're repeatedly doing something. You might be waiting for machine time, or you might be compiling multiple times, then running all in the same session or something like that. It's not the best use of your time. But it's also a little bit broken, even if you're trying to do something just as simple as 100 cores, because you get too much output. 100 things all printing at the same time. How can you possibly interleave and say, well, this happened before that happened? Or you end up with buffering of the MPI, and so when you thought you'd reached a particular line, or rather, when you thought you hadn't reached a particular line, because you didn't get a print statement output, you say, I haven't reached line 50. It turns out the buffering of the MPI, or the way the MPI kills the job off, meant that that message was printed, but never arrived at the screen. Or rather, so it was printed by the process, but was never delivered for you to see. So it can be very broken as a way of trying to get to the problem. Especially if we now turn and look at Titan and Mira. They're rather large. So 18,688 nodes. You don't have to use all of those, but even if you're on those machines, you're going to be using a reasonable number. And even if you're not using the GPUs, of which there are a lot, you could still be using up to 300,000 CPU cores. And were you to actually be using the CUDA cores, then if you think about it, you could easily have over 50 million ways of threads of concurrency in there by active CUDA cores at any one time across that whole machine. That's a lot of parallelism to be handling and trying to understand. And turning to Mira, at least everything is of the same architecture there, but it's still quite extreme in the parallelism with 50,000 nodes, 750,000 cores, and finally, if you were running an OpenMP on there, you could be over 3 million or pi million hardware threads, 3.145 million. So does printf really still work when you've taken it to that scale? Perhaps you could handle it at the small scale, but is it really going to handle it at the very large scale like that? Does it even work at 10% of that size? So what people tend to do is to reproduce the bug at a smaller scale, or that's the first instinct. So you try and shrink down from running on, say, 100,000 cores to having the bug just exhibit itself on 10 cores or 100 cores, something you can manage. So that's okay in theory, but in practice, it doesn't always work like that. So if you reduce the number of processes in the job, chances are you probably also have to reduce the data set. If you reduce the size of that data set, you might have and it was the data set that was causing the problem, then you may not trigger the problem again. And also, what are you doing running on Titan and Mira with a code that crashes on 100 cores? You shouldn't be using a machine that big if your code doesn't work at 100 cores. So you've already tried the code at scale. There is no bug at 100 cores. It's perfect. So you may be wasting your time there. Or is it a system issue? Is there something in the MPI when you get to those scales that there's something wrong with the system? I probably blame the system for a number of bugs over the years, and it's more often than not been my own code that's at fault, but there's occasionally times when the machines are playing up. And finally, and this is my favorite kind of example from debugging at scale, is the way probability adds up and just stacks up against you. So many years ago, we were starting to take DDT up to some extreme scales on the Cray machines. And the machines were working absolutely fine. We were able to debug 100,000 cores, launch a job, debug it, great. And then a week or two later, we tried the same piece of code, same debugger, same everything. Couldn't get a session started at all. It's very strange. The next day, every time we started, it would work. And it took a long time to diagnose this. In the end, we figured it out. We managed to get the debugger to a certain stage where it was able to print out exactly what was going on, or rather, to just stop debugging at that stage so we could see where it was. And what we observed was that the machine, when the machine had been up for a whole week, we could never start a large job on a 100,000 scale, 100,000 kind of scale. But if it had only been up for a day, we could always start. Now, the debugger has got nothing to do with the uptime of a machine. The debugger doesn't know how long the machine's been running. What could it be? It turned out there was a bug in the Cray MPI that was related to the process IDs of the individual processors running on a Linux machine. Process IDs go from 1 up to 32,767, then went round to 1 again. So a machine that had been up for a whole week had started a lot of processors on each of those nodes individually, and at any point in time, the chances are when you started running on thousands of nodes, that at least one of those nodes would be wrapping round from 32,767 to 1 again, at which point Cray would deliver the wrong information to us, and we'd try debugging a process that didn't exist. So it was the fact that 32,000 independent events, for example, would always produce, with probability of like as close to 1 as humanly possible almost, fail if a machine had been up for a week. Whereas, the machine's been up for an hour, none of them are wrapping around, it'd run every time. Now, if we tried to fix that bug on 100 cores, it would have taken a long time to have come up with a session where one of those 100 cores was having a process ID that wrapped round. But when I was doing it on 30,000 cores, every single time. So the probability may just stack up against you such that if you just keep trying to debug something on 32 cores, you're never going to see it. And you just try it out on a huge size, and it'll happen every single time. So use some machine time, save your own time is the message. So I think that debugging at extreme scale is sometimes a necessity. So that then brings about some challenges for tools vendors, specifically people like ourselves, and tools developers like we've heard from some of the performance talks today. We all have to deal with scalability. And that's all about producing something that's fast and easy to use. We have to deal with some complexity. Some of those machines are just not uniform anymore. This heterogeneity that's ever present now in large machines, accelerators, coprocessors, we've got to be able to handle that. But I think a third challenge is to make sure people realize that tools are there and that they're able to use them. So for us, the adoption of the tools is really important. So the ease of use and education is one of our challenges, making sure people can just turn to these things when they need them rather than their trusty printf friend that they've been using for so long and don't want to leave behind. So what you should be doing is expecting and demanding these kinds of things from debuggers. So you should expect a debugger that can scale to as high as the scale you need. You should also be able to support the platform you're using. If you're using GPUs, it should do those too. But finally, wherever this is installed, it should be well configured, it should be documented, it should be easy to get hold of and have the information that you need then and there so you can actually start using it. The last thing you want to do when you have a bug is to have to learn something and find out how to get something going. So at places like Argonne, like Oak Ridge, there are people there who are experts in these tools, in all the tools, not just debuggers, but also the profilers, and these site experts are there so that when you have a problem, you don't have to spend that day trying to figure out how to use something. They can actually, help you to get there. So there's documentation on DDT at both sites, and it's very well installed, and it's able to just work. And one of the reasons for that is that both Argonne and Oak Ridge have been working very closely with Allinea for a good number of years to basically satisfy those last three items that we can scale, that we can be able to cope with the kinds of programming model you're using, and then that it's easy to use and the information's there. So we started with Oak Ridge back in 2009 when Jaguar was in the middle of its procurement, and Oak Ridge had they basically looked at what was possible in debugging at around about that time, 2008, 2009, and debuggers weren't able to go beyond about 4,000 or 5,000 cores. As you increase the number of cores you were trying to debug, the slower the debugger ran, which was okay if you were only trying to work with 4,000 or 5,000 cores, but they were going to build Jaguar, which was going to have, at that time, I think it was 98,000 cores initially it was supposed to be. And they thought, well, we don't want to take something that takes a second at 5,000 cores and put it on 100,000 cores and then suddenly take 20 seconds. That's too long. That's not an interactive debugging then. That's rubbish. Let's improve that. So we started working with Oak Ridge to do scalable super petascale debugging, to put in an architecture that would let you debug a machine as large as Jaguar was expected to be. Ultimately, Jaguar got a little bit bigger. I think it arrived at 220-some thousand cores towards the end of that, but that was fine because we changed the game so much that it was actually possible to debug at scale in a way that was genuinely scalable, as I'll show in a minute. And now, of course, we see that has mutated into a GPU plus scale kind of system, so 300,000 CPU cores and almost 20,000 GPUs. We also started working with Argonne, who were going to put in at that point Mira, was on the horizon, shall we say, and we thought it would be really good if we could make DDT work at the scales we were showing for Jaguar and then would be Titan. We could make it do the same for the forthcoming Mira machine. Because the blue genes are a little bit different from a Cray machine in that they have a different architecture. They have what we call the I/O nodes and then the compute nodes. And the compute nodes are not running a full OS, full operating system, so we can't put a debugger there, and so it was interfering with our ability to produce something truly scalable. So we worked on adapting our method of getting scale such that it would work inside a blue gene, and so we delivered on that over the last few years, and now on both machines you're able to do this full-size debugging. So that's the net result of a collaboration that's enabled us to really make sure that you've got the tools you need to take your applications forward. After all, if you can't run your codes on the machines at scale, the machines are effectively not able to be used properly. So it's very important all the groundwork is in place, and that's been done. So a little story about little sort of background about the architecture of the debugger. What's underneath the DDT? It shouldn't come as too much of a surprise. If you're trying to get scale out of anything involving computers, it pretty much always involves a tree or some rather nice network of some particular architecture. So historically, debuggers had one GUI which had direct connections from every single node in a cluster. So as you doubled the number of nodes in a cluster, you doubled the time it took to do something like add a breakpoint everywhere or step everything. And that became painful, as I mentioned earlier, at 4,000 to 5,000 cores, but it was going to be absolutely, totally not possible if you were to be 100,000 cores. So what we did was we replaced that kind of architecture, put a tree in there, doing it properly for the machines that were about to arrive. And the tree is basically responsible for sending bulk commands, so the GUI would send a message saying, step all the processors into the tree. That's one message with very few number of bytes in it. And then that happens, it gets broadcast through the tree, and then the processors can step. And once they've stepped, they can bring back the information about where they are, merge that information back to the GUI, and display it to the user. So all of that is done with a tiny amount of network traffic, giving this scalability. It's actually logarithmic. You can step all of the processors on something like Titan and see where the processors have stepped to in your GUI in about 1/5 of a second or less. So that feels like you're debugging a laptop. You know, what we've managed to do is actually deliver debugging that is as responsive as what you're used to if you've ever used a debugger on your laptop, which means that, you know, suddenly printf, there's no need for it. So that's one aspect of what we did. The second aspect was, as well as being fast, it has to be easy to use. So the interface was really important. So we focused on designing and producing parts of the GUI that would actually work and didn't get any more complicated as you added more processes to the task. So our first look at DDT coming up. So there's a bit of, just to let you know that DDT is actually able to handle any of the languages that you typically use in HPC. So the C, C++, Fortran, UPC, or the PGAS kind of things such as Core, Fortran, that's all in there. We've got MPI, OpenMP, CUDA, offload for Xeon Phi, and so forth. So it's there, it's able to work with what you need. So let's have a look at what it looks like. So what does a debugger actually answer that printf can't just answer just like that? Let's say your program just crashes. Now on a HPC system, typically what that means is the job scheduler will send you an email saying the job aborted, failed badly, and that's it. That's all the information you'll get. But if you were to have run that inside the debugger, what you'd see is something a little bit more helpful. As soon as you code seg faults, or whatever the crash is, it'll stop. It'll stop before the process has been terminated, so you can actually see what's happening. That's the important thing about a debugger. It gets there before the processes have been killed off, so you can actually find out information about why it's died or is about to be killed off. So a segmentation fault would result in everything just pausing on this source code browser here, pausing on a line of the code, an error message coming up saying segmentation fault, processors 0 through to, in this case, 1199 have all stopped at this line with a segmentation fault. So that is so much quicker than just putting printfs and trying to find the exact line that something's crashed. And often that's enough, because you know exactly where it is. You look at the line, you say, oh, that's obviously why it's happened. And so some things are really evident. And you can also see things here, see if perhaps one process was doing something that none of the others were doing. This is how our GUI scales in terms of getting the stacks out of every single process. So the stack, i.e. the whole calling path of at this particular point in time, this is what 150,000 cores looks like. It's basically a tree and the number of processes at various points. So we've got 150,000, 120, all in this function that call this function, call that one. Then finally at the bottom level of the tree, one process is on a different line from all the others. So that might be significant. And so this is something that actually scales. If I was to add 10 times as many processors, I wouldn't get 10 times as much height in this or anything. It would just all fit onto this same kind of space. So imagine in that small amount of real estate, you can see everything that's happening in your machine. So that's very useful. And then we also have the ability to look at the data. So some of the things we've worked on are these little techniques for viewing data. So this is where are we now? Current line. So this is jcall, a variable jcall. And it's distributed across, each process has a different value of it. And this is a very tiny graph, a compressed graph of those values across all the processors. It's a big sort of squiggly mess, which means the values kind of have no pattern to them. My current value, probably can't read, is 36. It's colored green because it's different on other processors. So if you were looking for a constant value of jcall, and you saw that, immediately, without having to click through to every single other process in the job and see what they were doing, you can see that that's not what you were expecting. That could be a bug. This, as you remember earlier, I talked about the problem of the 32,000 process IDs wrapping around. We had another example of a bug where an MPI did something wrong that was breaking debuggers. we were being told that rank 7 was this one when actually it was rank 3 or something like that. We were getting the wrong ranks out of one of the MPIs, a temporary bug in one particular release. So if you did a graph of my rank, it would start at 0 and go up to maximum number of processes in a job, a straightforward diagonal line. And so we started trying to debug this problem. We loaded up an example where it was crashing all the time, or it was coming up with the wrong values, stepped a few lines inside DDT. All of a sudden, instead of seeing a diagonal line, we saw this squiggly line. So instantly we could see there was something wrong in the pattern of data. So these are the kinds of things you have to work on when you're trying to bring together all the state of thousands of processes and present something that makes some of the bugs kind of obvious. There are also a number of bugs such as those, the Heisen bugs, those ones that vanish when you try and look at them. Those bugs that just don't reoccur all the time. So there are certain things we can do, such as turning on our memory debugging, that basically force some of the sort of intermittent bugs to happen every time, because a bug that doesn't reoccur is one you can hardly fix. So if I start with a little local demonstration of just to show you what the debugger would look like, I'll just stop that presentation, drop out of that. Nope. About that. There we go, that's it. Now, bring up a new terminal. So a couple of little examples I knocked up. Well, actually, I borrowed one of these off Livermore. I'll just bring up the... Yeah, that's a good idea, actually. Yeah, okay. So to load up DDT on my laptop, I'm just doing DDT. Actually, yeah, just DDT, and then the application in this particular one, 7. I'll increase the font size of this one too. Appearance, probably could do something like that. That's a little bit more visible. So this is DDT's launch screen. Looks the same whichever system you're on, whether you're on a Blue Gene, or whether you're on an XK7, or your own little laptop, or a cluster. So this is an example of a code that just hangs. And let's just use it as a very simple way of looking at sort of DDT. So selecting the number of processes, then click Run. Make that full screen. Okay. So you can see the source code over here. It's very much like a standard modern tool that you would expect a debugger to look like, really, on these days. And you see in the middle, I need to increase the font size of the source code as well. Let me do that one. Code viewer. Okay. So that's actually a colored blue line saying that the processes are on there. So it's not coming up contrasting very well on the projector. But basically what this says is that all my processes are on this line, and as I hover the mouse, it tells me there are 8 processes on there, and it tells me what the ranks are. Over on the right, I can see the variables. So on this current line, I've got argc of 1, and argv is this pointer. Not particularly interesting. Here are some local variables. And these are those, this is that plot of the variables that I mentioned earlier. So task ID, constant there, count constant, number of things constant. But this is just 8 processes just ready to go. And they're at the MPI, just on the MPI init line. And I can step them but by pressing this button up here. And now you're seeing things are starting to move. This variable has just changed color. It's now blue, which means it's changed value since the last time I was there. Oh, right, sorry, last time I saw it, rather. So that's 8. Every process has got num tasks, and it's got a value of 8. Value changed from a very large negative number to 8. I quickly compared that across all processors. Yes, it's 8. I can step again. And you now see that task ID, which is the MPI rank, is this diagonal line from 0, MPI rank 0, through to the process. So this is the value of that variable across every single process plotted as a graph. Very simple, straightforward. I'll just play this. This program doesn't crash, so I'll just play it. What happens with it is it locks up. And what it's done is I've just paused it, so I ran it, it didn't stop, so I just pressed the pause button, and now it's put me in the middle of some part of nested deep inside OpenMPI. So let me go up the stack. Down here, you can see the bottom left here, you can see the call tree. There's one process that's down in MPI finalize, and there are 7 processes that are still in the broadcast. That's interesting. Why would that be? Let me look at the current line just to get some relevant variables. So there's an MPI broadcast from the buffer. Count must be the size, the number of bytes that I'm sending. An MPI int to root, which is 0 on MPI com world. Nothing wrong with that, except for the fact that count, I can see through my trusty graph, is different on all the processes. So what I've inadvertently done here is sent count to be task ID up here rather than 1, which was what it should have been, the number of bytes in it. So artificial example of a bug, but nonetheless, it's instantly able, by showing things obviously, making things more obvious when things are different, it's become easier to see some of the bugs in there. Okay. So that's a simple example, and let me take a different one now. Let's say you have an application that works sometimes, and then all of a sudden you just move it onto a large machine and it stops working. Has anyone actually come across that kind of problem where it works okay at 32 cores, then all of a sudden you move it up to something like Mira on 10,000 cores and suddenly it doesn't work? Yeah. It happens, doesn't it? Okay, good. So I've got one here that's a bit like that. MPI run minus NP8. So an 8 process job worked perfectly. Moved up to 32 processes. Okay, it's not finished. Now, I could just, what I could do is I could just start up the debugger, run that job again from scratch, and have another go inside the debugger and take a look. What I'm going to do instead is actually attach to that running job. So you can do this by you log on to the machine, see which jobs are running, attach them, and then you're able to go. So let me do this. So this means if it takes 2 days before your program decides to hang, you don't have to start again from scratch. So I just asked it to attach, and then it's found this MPI job is running. I'm going to attach to all the processes because I can, and then attach to loop. It's going off, it's connecting. And it takes a little while, and then they'll be ready. There we go. So this is those 32 processors. I can now see exactly where they were. So I've got, it's a loop where everyone just passes around a token, I think it's something like 50 times, or is it, it might be 50 times, and then once they've passed it round, they exit. What I can see is that 31 of the processors are in a barrier at the very end. You can see that because I could see they were in an MPI barrier there, but also by just clicking on this, jumping to it, I can now see they're there. But I have one poor little process that's still in the middle of a send. Okay, so that's interesting. Why is this one here? Well, to cut a long story short, he's only sending on things whilst the number of bytes received is 5 times. He's received 5 of them, he's sending 5. He's inside this loop sending something on, but whoever it is he's sending it to is just not sitting there and doesn't want to wait for it because everyone else has actually finished. That's interesting. So that's an MPI send. I can see my buffer size 1024. What has happened here is normally this program just terminates, it just works. But this time I've run it on 32 processors, it's not working, it's hanging, one process is sitting around waiting. Why is this? I've got an MPI send here. I had the MPI send when I had fewer processors in the job, but in this case the buffer size, the actual size of the packets I'm sending, is 32 times the number of processors. So it actually depends on how many processors there are in the job, how big the send is. And one thing about MPI send is sometimes it's buffered, sometimes it's not. It depends on how big your packet is. And at 1024 in OpenMPI, the default is that this should, 1024 times the size of an int, the default is that this is then buffered. So when I was running on a smaller number of things, it didn't matter that that final send wasn't being received, they just ended anyway. But once I've got beyond that threshold where it can't send it all in one go without noticing it, then what's happened is this final process can't finish until someone else has received the message, but there's no one there waiting to receive it. Okay, so that's the kind of power you've got inside a debugger. You can look at every single variable, you can look at all the variables in it, and you can really understand what's going on. It won't fix your bugs for you, but it will tell you an awful lot about it, so you can kind of understand why the behavior is as it is. And then it's your job to actually go and fix it then, given the information that's made available. So what I'm going to do now is then return to the slides, which are over here. There we go, from current slide. So I've shown a couple of examples of how you can deal with a persistent hang or a process count dependent hanging, attaching to a running job. I've got about 10 minutes left, I think, so. So I thought I'd do a couple of examples of things that we've seen in the past. Now this particular example, there have been others since, at very large scales of bugs. I know some of the codes during acceptance of Titan had to scale to full size, and there was issues that we were able to track down or at least help in move in the right direction by looking at it under a debugger. But there was one particular example that I really liked on Jaguar because of the fix being so quick when they put it inside a proper debugger. So the problem here was actually one of the guys working on OpenMPI itself, so actually on an MPI. And MPIs can be pretty complicated. If you thought that HPC codes were pretty complicated, MPI ones can be even more so. The actual MPI library itself has got so much going on inside there. So this particular code only failed on 98,304 cores. That was the only example that they found. Well, I'm sure if they'd gone any higher, they could probably have made it happen again. It seemed to be a different process crashing every time. So that immediately said, well, if I did use printf to fix this, which process would be printing out? Because I don't want to look at 98,304 pieces of output. Which process should I look at? Also, I don't know where it's crashing. There's a lot of things in this test case. I can't figure out where it is. So 98,304 cores would also be a long time to wait around in the queue to get that. You know, you can't just say, oh, can I have that many cores now? It doesn't work like that. You know, you have to ask people very nicely to get special reservations and then use that time very wisely. So I needed something that would actually work first time. So what actually happened was we ran the code, we fired it up inside DDT, and the code ran. One of those cores segfaulted, and that very screen I showed you earlier with the dialog coming up saying your processors have segfaulted just showed him that core had segfaulted, and he could see from looking at the variables that were being displayed that one of the pointers was 0, was null, a null pointer, and on this particular process it was null pointer. He knew exactly what the problem was. He wasn't guarding against that null pointer, and he could go off and he could fix it. So fixed that within 30 minutes. Now, that would not have been possible without the debugger. So how can you avail yourself of this wonderful magic? Well, getting started on Titan is very easy. module load DDT. Then type DDT. That's it. Okay? You're ready to debug. Now, just to prove this, I'm going to have a go myself. Now, there are a few more steps involved because of the network, but let me just do it anyway. This is actually the remote client. DDT has a remote client you can download for your laptop or your Mac or your Windows machine and just connect to one of the systems and start debugging. So here's what it would look like if I was sitting inside Oak Ridge and I was debugging, but actually I'm doing it on my laptop here. Oops, I don't want to open in P. So I select, maybe my font's too big. Selected 160 processors running on 10 nodes. I'm going to log into Titan and actually just see how busy the queue is, because I don't want us all sitting here for hours waiting for something to happen. Okay, well we should get 10 nodes pretty easily. I'll just go for 10. I'd probably turn out my user was not allowed to have it or something, so I'll just stick with that. So I click submit. What's going to happen now is DDT is going off, connecting back to Titan, submitting my job, and then hopefully it'll start. Now, of course, queues being queues, it might not necessarily start straight away. You can see that actually what's happening is DDT has submitted my job to the queue, and all I need to do is sit back and wait for it to start. So whilst that's happening, because it's not particularly that exciting to wait and watch for those things, let me kill off that one. We don't need to see that anymore.
Will you be able to run on Vespa?
Yeah, it would be, yeah. I don't think it'll be too long starting. The queue was looking pretty good. Yeah, it's still waiting. But whilst that's happening, let me talk about... Still at it? Yeah, it'll do it. Where's my virtual machine? Ah, there we go, it's starting. Okay, so obviously it's only 160 processors. It's not 160,000. But you know, hopefully you've heard enough of me today that you can take it on trust that it can do that. But when you actually need to do 100 and some thousand cores, just press the button and away it goes. So what we have here is 160 cores, ready to debug a particular problem. And this particular problem is very simply doing some calculation, getting the wrong answer out. So I'll just move down to the end. So this is what I would do, is typically working through a code like this. I would set a breakpoint, that's easy done. Now breakpoint is somewhere where you say, right, when you're debugging, run to this point and stop. So here we go, play. It tells me it's run to this breakpoint and stopped there. So it allows you to say, if I think it's this particular function that's got a problem in it, just click, set a breakpoint there, run to it. Okay? Very straightforward, very easy way, much easier than putting a printf in something. So but what I'm actually going to do with this one is run all the way to the end of the code, because at that point I'm going to find there's a problem. What I'm doing is calculating a sum, reducing it across all the processors, and discovering I've got a nan. So there are many things you can do with the debugger. Debuggers are like, they're a toolkit, and you don't need to use every single feature to discover every single bug. But one lovely one I find is this ability to look through an array for a value that's dodgy. So if you have a nan as a value, then that's on a sum. This was created by a reduction up here, MPI reduce, sum, final sum. So I've obviously got a nan, it's come in from another process, so let me click on that and see what that looks like across all the processes. You can see that this is compared the value of a variable across all the processes. And it's easy, even at the full size of Titan, to scroll across. This is something we've managed to do in again, about a tenth of a second, even on the full size of a machine. So I can see that the final process in the job has got a nan in it. Okay, how did that come about? Well, again, I'll take another shortcut, and what I'm going to do is look at the elements array view array. So there's a tool here for looking into your arrays. I remember it's something like size is 32,001 elements. Where have you gone? There we are, 32,001 elements, so I've got 32,001. And what I want to do is evaluate that, but look at all of the processes in the job, so all 160 of them, search through and find which value in that array is a nan. It's going off, only 160 of them, so what it's doing all of this in parallel. Whoops, it didn't like that. It goes off, looks at all those, filters them all out in parallel across the size is... no, I've got the wrong size of elements. Again. N is the number of elements, not count. So because this is happening in parallel, it's as quick on 1,000 processors as if I had 100,000 processors. Except it's not doing it at all. Must be a feature. Oh, maybe it's because I got this one open at the same time. Yeah. Oops. No. Wireless down. Okay, so yeah, it's disconnected itself. That was it. So yeah, even without a network, it's very difficult to... Great. All right, so that disconnected itself rather nicely at the right time. Okay, so let's go back to the slides, the last 2 or 3 slides now. So it's SSH over, so no, it won't reconnect. I'd actually have to go back in there and kill it, but I didn't book it for long. Problem is, I can't SSH in. Okay, so what that was going to do was just find me the exact element in the array that was a nan. So I mean, that's pretty useful, pretty powerful. So we had another example. This was on Mira. This was 16,000 and some cores. Code ran all right until it got to those numbers of cores. All of a sudden, it stops working. Okay, so the code had been abandoned. The bug couldn't be fixed. There was no way of debugging it. It was also too busy a machine to do interactive debugging. So there's a mode in DDT we call offline. And what this does is it basically runs under a debugger and logs things as they've happened. And you then review the HTML log file afterwards and say, oh, that's why it crashed. Getting started on Mira is just the same as on Titan. Straightforward, simple, well installed, ready to go. Soft, add, plus DDT. DDT, you're ready. Okay, and what we did in this particular bug was we submitted the job in offline mode, and we ran it, submitted, forgot, came back on the Monday morning, and it suddenly had time to run 16,000 cores. Came back, we looked into this HTML log file, which basically said that there was a segmentation fault in a certain number of the processes, and then this is like effectively the window you could see in DDT of the parallel stacks, but it was showing you that which processors had died at which particular points. And so from that, we were able to detect that the problem looked like it was coming from inside the IBM's MPI library. We didn't believe that, though. So we subsequently went back in, and we turned on that memory debugging I talked about. So memory debugging forces, as soon as you've had a bug, it forces it, in terms of accessing memory beyond the end of an array, it forces it to happen. And that's, so we ran it again, and we were able to actually detect that a particular variable was being initialized incorrectly, and we were able to, actually find the exact point at which it went one element too far in an array, and then detect why, and then go forth and fix that. We did that by putting things we call trace points in there, which are scalable versions of printf. So it allows every time you pass a variable, pass a line, to print out a variable value, and it's merged scalably. So this is printing MPI rank from a multiple thousand process job as we pass particular lines in it. So you say to the debugger, just print every time you pass here. It's a way of doing printf without having to recompile. And I'm not going to do the interlude with that without a network anyway. My top 5 features: the parallel stack view, Find where all your processes are in a glance, that small part of your screen. Great for finding when something's doing something different. I can't tell you how many times sparklines, these little plots of graphs have detected a problem for me. That one, parallel array searching, pretty useful. That's certainly helped people out there on the streets, but it's always very important to be able to still step, play, set breakpoints, control the code and make it do what you want to do. And then finally, that offline mode. The one problem about large machines is there's only like one number one machine, and if you want to use all of it, you can't expect to have that at 3 p.m. on Wednesday when you've got a bug. Sometimes you have to submit your job to the queue, let it run, let it debug itself overnight, and then review the results. So in summary, debugging at scale isn't difficult. It is there. It should be as easy to debug at 300,000 cores as it is as 30 cores. So we've got an interface that works for that. It's also not slow. Because we've got that tree, then you can do things in a tenth of a second or in a second or less that you would expect to be able to do with a laptop. And then finally, this is actually stable, it's out there, it's in production, it's well used, it's well supported. So when you ever have a problem with anything, there are people you can contact, not just in Argonne, not just in Oak Ridge, but also ourselves at support@allinea.com. Any problem you have, we're really happy to help you on that one. Okay, that's it. Thank you. How is DDT different from TotalView? Well, I tend not to like to answer that question really, because I don't think it's fair to do so without TotalView here to answer it for themselves. But that said, no. I think what you'll find in DDT is a modern, easy-to-use tool that we think does everything that people need to do their debugging at scale. And try it. If you like TotalView, that's fine. Try DDT as well. Not going to say bad things about I have friends working there. So the question was, I said we had CUDA support, but can you actually debug inside of a CUDA kernel? That's a very good question. The answer is yes. So very simply, it is almost like debugging regular code, except it's not as fast as debugging regular CPU cores. But you can do things like set breakpoints inside a kernel, so you can make it stop at a particular line of a kernel, then look at each CUDA thread individually and take a look at the variables inside there. So yeah, that can be done. And we support the CUDA compiler, the CAPS HMPP OpenACC compiler, and the Cray OpenACC compiler as well. That's right, yes, you can. Sorry, you can debug inside OpenACC kernels. Okay.
What PGI support?
At this point, the PGI compiler is what we call a source. So the question was, what about PGI compiler support? The PGI compiler inside the GPUs is source to source. That means it takes your OpenACC or it takes your Portland CUDA Fortran, converts it into CUDA-C, and then sends all that off to the CUDA-C compiler for the CUDA-C compiler to compile. So that means when you see it inside the debugger, you only see the middle bit, that automatically generated code. So unfortunately, all that information that was in your Fortran or your C that you understood was your code, it's lost. You only get this sort of intermediate machine-generated CUDA, so it's not that useful. You might get some things out of it, but it wouldn't be the most helpful thing you've ever seen. It's a good question. So the question is that what we've seen in the demonstration was how codes doing most of the same things look quite easy to view when you're doing scalable things. How is it going to look when you've got really asynchronous codes doing really different things? Yeah, it's a good question, and in practice, I think that people have found that the divergence in those stacks that you see is small. If it's a climate model with lots of different things, then what you see is, say you're doing 5 different parts of the atmosphere, ice, sea, whatever. They would each of them be in little subsets. So you've got one tree in this part of the code, one tree in that part of the code. And the guys in Livermore have a tool called STAT, which does parallel stack view. Well, effectively gets the stacks out of all the processes. And they did and does very similar merging kinds of things. And they looked at pretty much every application that they were dealing with, and they found that the most sort of differently categorizable classes of processes in any job that they came across. It was like 5 or something. It's like kind of a handful. And that was a few years ago, but yeah. So generally, they tend to be doing the same, but yeah. Okay.